Bonjour, Malalava, Iorana. Uh, Thank you all for coming after that wonderful lunch. Let's get right into it. As Jenny was right, I did have the longest title in the conference, but I shortened it just to spite you. So today we're talking about the population rise being the proximate origin of the Polynesian chiefdoms. Let's get right into it. Let's see. So I think this question here on the screen, how do we explain the evolution of institutionalized hierarchy in Polynesia or hierarchical society? I think many would probably think this has been adequately answered in many parts of Polynesia, but I would say, well, we could debate that, but I would say not so in Samoa. The answer in Samoa has implications for the rest of East Polynesia. So that's why I'm here today. And I've been running a project in the Whalefa Valley on the island of Upolu for, well, several years, but it's been delayed for several years for obvious reasons. And we just got back to doing field work last month for the first time in almost 3 years. So, and that project in Whalefa is designed to investigate the origins of hierarchical society in Samoa. So, and things here. Our project answers that question by investigating these two, well, the chronology of these two cultural innovations that I have on the screen here. They being many folks have argued that these two cultural innovations are kind of a spark that led to increasing hierarchy in Polynesian societies. The first one there being changes in land tenure or changes in the control of access to land and what can be done on land. One cultural innovation. And the second one that I've listed there is agricultural change, or more importantly, agricultural intensification, something I think we're all pretty aware of. And so the project I've been working on is looking at the chronology of these two changes in the valley on the screen there in Whalefa, and a close-up of that valley is the bottom picture. So I'll be referring to the valley, and this is what I mean. So I'm going to jump right into results. And so the first thing I'm going to talk about is the chronology we've been able to generate for various kinds of rock walls, or various, and I'm kind of interpreting rock walls as measures of changes in land tenure. So people who work in Samoa, we've known there's been different kinds of walls for a long time. And I'm going to just kind of gloss these as small walls and large walls. So they're called different things by different people. But small walls, a picture of which is on the bottom there, those are generally, well, they look like that. They enclose empty areas, perhaps used for gardens, or they enclose small platforms and create perhaps what Jesse Jennings called decades ago household units. Large walls, in contrast, those are also called sometimes raised walkways or even double walls. Those are often 2 to 3 meters wide at the base. They may be a meter in height. Often they have a meter wide kind of cleared pathway on the top. And you see on the upper picture, that's one of these large walls. You can't really see its height in that picture, but you can certainly see the kind of pathway on top of it. So these two kinds of wall types proposing to you today that they measure different kinds of behavior. Large walls are more group construction projects. They certainly require a different kind of labor organization than the smaller walls, which could be, if you want to think about it this way, could be made more in terms of, made by family units, let's say. The large walls also can span kilometers in length, and I'll show you pictures about that in a minute, where they span the width of this valley. And so the origins of these walls, the chronology of walls, I'm linking to changes in land tenure, right? Changes in how land is divided and perhaps the kinds of things that can be done on that. So let's look at that chronology. Sorry, one second before I do that, though, I will show you the distribution of some of these things in space. This is a satellite image of the Whalefa Valley, and the faint lines there are rock walls that were identified through manual feature extraction from LiDAR data by my co-author, Seth Quintus. They're all across the valley. The kind of orangey faint lines there are these rock walls. The faint purple lines are ditches. The bolded features are ones that we have ground truth using GPS pedestrian survey, so walking out across the landscape. So you can see the yellow walls are the small ones that I talked about earlier, and the red walls are the large ones that we, again, the large walls and the ones we have ground truth. You can see that some of those red walls, they, in our GPS kind of pedestrian identification, they don't necessarily span the valley, but that's because we have not been able to look at the center of that valley. So you can see some of those red lines, they kind of go from one side of the valley to the other with a hole in the middle. But many of those lines, those walls certainly cross the entire span of this valley. So different wall types as a way to look at land tenure chronology. Here is some chronology that we've been able to develop. So the age ranges for these walls are based on multiple radiocarbon dates per wall from different layers, taking those radiocarbon dates on identified taxa and putting them into OxCal models, both multi-phase models and single-phase models, which generally agree in the ages of these walls. So our kind of model structure is not unduly influencing the age ranges we arrive at. I didn't realize that that graph there on the top, I mean that on the screen is kind of hard to read, but in general, the large walls appear first. Those are the ones I've kind of bracketed in red just to draw your attention to that. And they first begin to be made around 900 years ago, but that construction accelerates around 600 years ago. Shortly after that, we have the smaller walls starting to be built. So this is some of the first kind of widespread chronology we have on these rock wall construction in Samoa. Again, earliest at 900, that's that single wall on the top really. But then again, with increasing frequency, walls are built after about 600 years ago. We can look at the median ages of these things, and they are different. The large walls and the small walls have different median ages of about 500 years for the large walls and 300 years for the small walls. We've also looked at bonding and abutting patterns in the field, so how walls hook up, and those bonding and abutting patterns also support this kind of more absolute chronology. And although it looks like there might be different sets of walls here, those kind of most recent 4 walls at the bottom, looks like they might be a single set of things made around the same time. They're not spatially associated. So these walls appear all across the valley at these various time periods. But again, beginning 900 would be early, more like 600 years ago, and then accelerating. So first, this is the kind of first seen changes in land tenure in this part of Samoa, again, at about this time period. Right, let's move on to some of the data we so far have on agriculture. Right, 2 different kinds of data on agriculture, or more specifically, I should say, environmental change. First off, in the valley, we have evidence of forest burning, and that comes from 2 widely separated stream sections in the southeast quadrant of that entire valley. So you can see on the top there a picture of a really dark charcoal layer at the bottom of that stream. And indeed, that's what we have investigated and dated, and it's chock full. It's jam-packed with Alarites, charcoal, and nuts. So Alarites in Samoan, it's llama. In Hawaiian, it's kukui or candle nut. So the kind of widely separated deposits date to about the same time. In a Bayesian model there, I have the modeled age range from about 680 to 336 is when this Alarites burn-off occurs. I'll pop back a slide and show you that's what that green date is up there at the top. That's why I kind of singled that out. So we know that something is going on around 600 years ago or so. People are removing a Alarites, I'll say forest, but maybe too grandiose a term. Alarites trees are being removed through burning from at least parts of the valley. There is not an Alarites tree in the valley today. I've never seen a single one, and no one I've talked to has ever pointed one out to me. So it looks like this kind of tree crop was removed, as I said, 600 years ago. So certainly a change in agriculture, a change in what's being cultivated at that time. The second set of data I have on agricultural, or again, more generally, environmental change, comes from geochemistry and sedimentological analyses from some dissection cores we also have back in the valley. These images there on the screen, there are various sedimentological and chemical data, and I'll just talk about them briefly, but I'll draw your attention to the red lines there. Those are dates we have from these cores. The red line on your right, That's a date of 3,500 years ago and just radiocarbon years. So calibrated, it's about 1,000 years before anyone ever got to Samoa. So it's old. The red line on the left is dated to 693 plus or minus, and I have the calibrated date there on the screen now of 670 to 560. So at 2 sigma. So these D-section data, we really we can see, I'll go through it, but you can see the changes to the left of that more recent date, changes are occurring. And that's the same time we also have this burn off of allovarietes in the same area. So some of those changes, many of you might know about these kind of data, how we interpret them. The top is loss on ignition, so this amount of carbon material in the sediments, and it's very low until you get to the most recent 50 centimeters of the core. And that's just the contemporary modern peat layer. Potassium and calcium, those increase after about 670 years ago. That's almost certainly, we propose, due to kind of upland forest clearance and increased weathering of those minerals out of the basalt bedrock and their deposition into the basin, this Folival basin. Lastly, we have magnetic susceptibility, or MagSus. MagSus measures the amount of mineral, pretty much iron-rich mineral content in these sediments, and that too increases after about 670 years ago. There are, of course, massive spikes in MagSus at other times, particularly pre-human. Perhaps that's due to increased rainfall at different times, but we don't have data on that yet. All told, data on the allovarietes burn-off and the geochemical and sedimentological data from these cores suggests that there's certainly changes in the environment and what's being grown, I'll just say roughly around 600 years ago. So this data is 670 to 560, as I said. What they were growing after 600 years ago, I don't know. We don't have any data on that. We're still looking at the microfossils in these cores. I mean, suspect it'd be taro, but we simply don't know. Okay, the last thing I'll talk about in terms of results, before I tie it together, is changes in population size. And from an article that came out a couple of years ago in PNAS, my colleagues and I looked at changes in population size by analyzing modern Samoan DNA. I won't go into the specifics of it. There's people here who know much more than I do about that. But what I can say is that looking at these data, we can estimate a small founding population in Samoa of about 3,000 years ago, and a population between 700 to 3,000 people is the estimate. That grows very slowly until about 1,000 years ago, or 30 to 35 generations, when you have a spike in population up to about 10,000 people. Then there's a crash at European contact. So this is the first kind of genetic estimates of population size in Samoa that we have. So interesting things going on here. Very interesting things going on here, and I will put that together now. We have some kind of landscape transformation and new things being cultivated at 600-ish years ago. We have changes in land tenure beginning 900, but also more accelerating 600 years ago with those rock walls of different kinds being built. And both of those things are occurring after this sharp rise in population. I'll say 1,000 years ago, and that's taking a 30-year generation time, but really it's 30 to 35 generations ago. So that's kind of the sequence of change here in this part of Samoa. Now, I want to point out that those changes all occur in Samoa roughly after East Polynesian settlement. Or I have a question mark because you could also put contemporaneous with, I think, but right around the same time. My main point is that the changes that I've identified here in Samoa are not well before settlement of East Polynesia. They are either contemporaneous with or afterwards. Why does that matter? Because according to my argument, at least what I'm proposing here, is that this suggests there's some kind of convergent evolution between West Polynesia and East Polynesia in terms of changes in land tenure and new agricultural strategies, perhaps including intensified agriculture. And if those are indeed the kind of sparks that lead to more hierarchical society, we see that being, at least in this proposal, independently invented in West Polynesia and East Polynesia. And that's not something new. Others have, particularly Pat Kurtz right here, he's talked about that there's a variety of things we might see as adaptive radiation in East Polynesia, but a variety of other things we might see as convergent evolution. And I think this is just possibly a case for us to investigate in terms of convergent evolution. That's all I have for today. So I have my Samoan, thank you, because I work in Samoa, Papelava. I'd like to also thank these funders and people. And actually, I would like to, thinking about the discussion this morning of the kind of conference that took place 22 odd years ago, I'd like to dedicate this paper to Jeff Putzi, who was at that conference 22 years ago and is not with us today. So thank you.